Now we're going to see what else we can do for spatial data with software, with the R software, by using geostatistic tools. So now we're going to use the package that we're introducing today. This would be the GStat package, Joint Statistics. So I'm going to upload everything, and I'm going to show you some of the help points. This is also a very complete package. It allows to do many things. You got the variogram, spatial prediction, cross-validation, interpolation, or trig. That's something that we're going to see today. So this is part of the help content. So let's begin by reading the spatial data. We're going to use this data set that we have with all of the information of the limits and the yield. In this case, we are going to use just the limits, and we'll also read the yield data that we have in a CSV file. These are specific points about observation and the partials for production on the field. So let's read the CSV data here. And this data has 665 observations from 3 variables. And the 3 variables are the X, Y, and yield variables. So I have the 2 spatial coordinates here. And I have the yield. It's very simple. That's the minimum requirement. And I'm going to transform this information that's in a table and transform into spatial data. And to do this, I'm going to use this function of the package. So first, we're going to have the table and also the coordinates, the X and Y coordinates, and then the system to project the data. I know it's in the same one, this one, and the file for the limits. And so I'm going to use the stcrs function based on the limits to create the spatial data and to see what else we have. So we're going to create a map. The first one shows us the limits, the borders of the geometry. And then I'm going to choose the yield, and I'm going to add it to this map. So these are the observation points that I have, my 665 points of observation. They're located in this area. And the next step is to create a raster that shows the area of interest with a resolution of 10 kilometers or 10,000 meters. So I'm going to work on this limit, and I'm going to create this raster. And we can see how it looks like here. So I have 38 rows and 500 cells. I could use a better resolution in this case, or a lower number to have more cells and to be able to see more detail, but this is going to take more time. So for time's sake, we're going to maintain this resolution, but depending on the type of analysis you want to carry out, this is going to change depending on the scale that you use. The next step is to create a formula that will define what the yield depends on. In this case, the yield is a function of a constant average of the area. Sometimes we have to use a function for the coordinates like x and y, or a combination of both. Or you can also use some other variable like elevation. And there are other methods that can be used here also. But the simplest thing to do right now, where I assume that the average of the whole field would be the same. So now let's create the variogram. This is going to give us the calculation of the variation between the different points. And first we have to define how these points are going to be gathered. So this is the step, the 10 kilometers and the maximum limit that's here as 130 kilometers. So I'm going to run this, and it's going to create the variogram. And it tells us that it has 13 observations and 6 variables. And I can create a plot of the variogram, and this graph will show me the 13 points that I have available for every distance and what's the value of that variability or variance. And there's a spatial dependence. The values that are closer have less variability to the ones that are further. And this is what you expect in data that have spatial dependence. What I want to do now is to create a theoretical model that's going to show a line that has the best adjustment or that's better adjusted to all these points. So I'm going to create a model here. I'm using some parameters based on the graph. So I'm going to use number 4 here as the value of the sill, and probably my model is going to be exponential. This is the range or scope. It's approximately 20,000 kilometers. And my nugget would be the dot effect is going to be close to 1. These values are just a first estimate for the optimization process that the software is going to run. So we don't have to be too concerned with these values, but they have to be reasonable. And nevertheless, I'm going to adjust the model to the experimental data that I have available. So I'm going to use the function feed variogram, and this is going to do the adjustments. The original values are going to change and going to be replaced by values that make more sense. And I'm going to do the plot here of this model. So I'm going to verify, and apparently it's properly adjusted. It's very close to most of the points. If I want to see the values and how much they changed, I can use the m variable, and we can see the dot effect here. 1 was very close, and the maximum value was 2.9, because this value would be just this part. It's more of the dot effect. That's why 4 wasn't a good estimate. And the range is here close to 50 kilometers. So these parameters many times will be seen in articles that are reported and that analyze spatial data by using geostatistics. And these values have to be reported in order to be able to compare one area with another and to define if you want to do a sample process or not, to see what are the minimum number of points. The variogram wouldn't be the final goal. It's also important to have the prediction, and that's what we're going to do now. So I'm going to create an interpolation model here, and this one has the formula that depends of a constant average or mean. I have my data here. These would be the points. I have my model, which was the model that I adjusted to the data. And I'm using this argument of the maximum number of neighbors, or nmax. With 100, the result won't change that much, and this allows me to do calculations in a faster way. So in order to save time, I'm using this parameter of 100 as maximum number. Now we create the model, and this is the most interesting part, which is the prediction. So I'm using this function called interpolate from the raster package. So the first argument would be the raster that we created with the resolution of 10 kilometers. And then I have the interpolation model that's going to take the values that already exist in these points, and they're going to interpolate it on the raster. So I create my prediction. The raster has very few cells, so it's going to be fast. And the model can also estimate a second variable that would be the variance or variability. And this allows us to understand how much we can trust that prediction, and where there are uncertainty points. And this allows us to visualize everything in the map. The first map that I'm going to visualize would be the grass interpolation. And the raster was created on the spatial window of the limits. So if I see the raster, I can't see that much. So in order to improve the map, what I'm going to do is to use the mask. So this mask can be used as a layer, and you can use the polygons of the limits. So everything that's outside the polygons is going to be left as an NA, not available. And after I have a raster with the mask, you can also use the raster as a mask. And this operation is a little bit faster. So I'm going to compute both of them here. And now my prediction will be here. and it's going to be focused on the area where the polygons are. And finally, I'm going to prepare the maps here for visualizing them, and the map will contain my value of the prediction that's already cut. It also contains the geometry, which are the borders of the polygons, and the points to see everything at the same time. So these are the point values, and I only have one scale. It would be interesting to have two scales to be able to compare, because these are different color scales. And the base function of the plot is not the best one to do complex maps. So I recommend to use other packages like the TMap, or you can use the QG software to do the maps. But just to have a fast visualization, it's okay. And I'm also going to see the values of the variance. We can see that this part to the east has a high variability. The uncertainty in this case of the prediction is very high. I cannot trust too much what I'm seeing here. So this is the geometry and then the points. Now I think it's very clear that the uncertainty is directly related to the geometrical configuration of the points. So where I have a very large distance from the point, the uncertainty also increases. There's a high uncertainty because those values that are being estimated are on the limit of the reach of spatial dependence. So I have a very high dependence in this case. So once again, I'm going to use the right raster function to save this data in this file, in this TIFF file. And by this, we finish this spatial correlation by using the SPDEF and GStack packages in R.